So before we get to today's topic, we should do a quick review problem. So your company is making a special tetrahedral widget. So a tetrahedron is sort of like a three-dimensional triangle. So it looks something like, I don't know, something like that. All right. Well, now what happens? Now in this tetrahedron, in one corner, the three sides which come together all form right angles with each other and have lengths of 6 centimeters, 7 centimeters, and 10 centimeters respectively. So this is probably not quite the right picture because we say, okay, look, there's a corner. In that corner, everything has right angles. Like, oh, those are our favorite kinds of angles. We like right angles. And so how can we think of it? And so the way to think of it is to say, well, we can think of it as though it could fit into a corner. So we draw a nice little sort of corner space. And we could say, look, let's put it so that that corner fits right here at the origin. And then we have those three sides that form right angles. Well, the nice thing here is these are all right angles. So that's why this is going to fit so well into this corner. And then we say, okay, look, there are 6 centimeters, 7 centimeters, and 10 centimeters. Well, of course, the question is, which one is 6, which one is 7, which one is 10? And the answer is, we just pick. So it doesn't matter. So let's say it goes 6 out in the x direction, 7 out in the y direction, and 10 up in the z. So now what we can say is our tetrahedron, we actually have a pretty good picture. It looks something like that. Okay, so there's our tetrahedron. Now, continuing on. Oh wow, that's a lot of responsibility. Okay, you are in charge of making sure that you get the right amount of materials to cover the surface of this tetrahedron. So determine the total surface area of this widget. Now the nice thing is that when we look at this shape, we say, look, it's a tetrahedron, it's a three-dimensional shape, but in terms of the surface area, we just have to look at what's on the surface and what type of shapes are involved. Triangles. Lots of triangles. So really we have to find the area for triangles. Now some of these triangles are pretty easy because if you look on these three back triangles, they're all right triangles and they all have nice lengths. So for example, this triangle on the back side here has one length, which we can call the base, that's length 6, and the other, which we could call the height, is 10. And so we could say that this triangle on the back side, that area is 1/2 times base times height. On this side next to it, which we would say, well, it's in the YZ plane, similar process. On there, well, base would be 7, height would be 10. So 1/2 times 7 times 10. And on the bottom, we have, again, a nice right triangle. Base would be 6, height could be 7. So 1/2 times 6 times 7. So those three are pretty straightforward, no surprises. But then we have the slanty face. That's not quite a technical term, but you know what I mean. The other side, that one that's going to make us have to say, And the challenge is, it's not so clear. How do you find the base? How do you find the height? And the answer is, we're not going to find the base or the height. We're going to say, let's use our tools. So again, we're to the point where, look, all that we have to do to finish up is find the area of that face. Well, to do that, we can use our tools. So what's our tool for finding areas of triangles? The cross product. The cross product can help us find area because the magnitude of the cross product has that geometrical interpretation as area. So in particular, we say, look, let's first identify these points. This is the point 6, 0, 0. Over here, this is the point 0, 7, 0. And up on top, that's the point 0, 0, 10. So those are our 3 points. Now, are we ready to take our cross product? Yeah, we're not ready to take our cross product because we have points. Cross product requires vectors. So we make vectors. And the way we make vectors is we just say, let's choose a corner and find the vectors coming out of that corner. It doesn't matter which corner you choose, so I'll choose the one over here. Say I want to find these vectors here. So the one that goes from 6, 0, 0 to 0, 7, 0, well, you just need to know the difference, because that's what vectors measure. We went down by 6 in the x direction, up by 7 in the y direction, and our z stayed the same. On the other hand, if I go from 6, 0, 0 to 0, 0, 10, I'm going to go down by 6 in the x again, but this time the y stays the same, and we go up by 10 in z. Now we have vectors. They're nice three-dimensional vectors, and therefore we can take the cross product. And so we'll write that down. That's I, j, k, negative 6, 7, 0, negative 6, 0, 10. And, all right, so let's see. I times 7 times 10, 70i. J times 0 times negative 6, that's 0j. K times negative 6 times 0, that's 0k. Negative 6 times 7 times k, well, that would be negative 42k, but because I'm going now in the other direction, that's going to become a plus 42k. 0 times I is extra 0e, so that's 0i. Going to subtract that. 10, negative 6j, that's negative 60j, and because I'm going the other sort of uphill direction, if you will, I subtract that, that becomes plus 60j, giving us a grand total of 70, 60, and 42. All right. Well, there you go. There are the numbers. All right, so what do you get? Well, so the area of the missing side would be the square root of 70 squared plus 60 squared plus 42 squared, which, because we don't have a calculator, we'll just leave it as that. That's okay. Now, that's just the area of that one side. What's our final answer? Well, we put everything together. A half times 6 times 10, that'd be 30. And a half times 6 times 7, that'd be 21. And half times 7 times 10, that'd be 35. And then plus this big number, whatever it turns out to be. We could spend time to chip away at it, but we don't need to. And there's the area. Now, normally I don't care about units, but if I wanted units, what would be my units here? Centimeters squared. Apparently I've made a mistake. What's my mistake? Oh, you're right. You're right. Thank you. Because the cross product is the area of a parallelogram. The area of a triangle is a half. Thank you. Thank you. Good. Good. Now, if you don't like that half, you could actually do a little bit to get rid of it. But that's okay. All right. And now we're good. Now we're good. And centimeters squared. Okay. If we ask for units, include units. If we don't ask for units, well, you can include them or not. It's up to you. All right. So why is today so important? What is it about today? Well, the answer is today we're going to be talking about our flat thing. So I guess I should say our two variations of flat things. Now, our first variation is lines. And we know how to deal with lines because we dealt a lot with them before. And when we deal with them, we say, well, if I need a line, I need two things. I need a point and a slope. Now we say if we want a line, we have to get two things. A point and a direction. And so the direction is sort of saying, okay, from your point, which way is the line going? So in some sense, you can think about that's what a slope is doing. A slope is telling you something about the direction of the line. So we have to have some point that cements us in space somewhere. And now, once we have that point, we can say, well, we move in a certain direction. Okay, so remember, if you're ever asked to find a line, you always say to yourself, all right, I need a point and a vector. Normally, the point's the easy one, so it comes down to saying, what's the vector? Now, how do we actually write the line? Well, okay, let's think about what's going on here. What's true is Suppose I'm some point. So let's suppose I'm a point up here, x, y, z. If I'm a point on the line, then if I look at the vector from x0, y0, 0 to x, y, z, and it's right here. It's x minus x naught, y minus y naught, z minus z naught. So if I look at that vector, it has to be parallel to the vector that we have for the line. So to say it's parallel to means it's a multiple of. So the vector between my initial point here and an arbitrary point there, that vector is some multiple of the direction vector. Now what you can do is you can rearrange. And so if you rearrange, you get the following. You can say, if I think now of my point as being represented by a vector, so just temporarily, I'm just thinking of like, okay, I'm going to represent a point by a vector. It's not such a crazy thing to do. Then x, y, z has to satisfy the initial point, x0, y0, z0, plus some multiple of the direction vector, t, a, b, c. We call this the vector form because it's vectors. And it's kind of intuitive. It says, look, you start at your initial location that you know is on the line, and then you move some amount in the direction of the line. And the t is allowed to vary. And so as you let t run over all possibilities, you're going to capture every possible place you can get to on the line. Now, this is just one way to write a line. There's another thing you can do is to say, well, I know that vectors work by components. They work entry by entry. So let's look at each entry and see what's happening. As an example, if we look at the first entries, on the left we get x. On the right we get x0 plus t times a, because this t is scaling. And we can do that for every entry. And if we do that, we get what's called parametric form. So x is x0 plus a times t, y is y0 plus b times t, and z is z0 plus c times t. And this is sort of, I like this form. One of the things that's really easy is if you look at it in this way, where you have, okay, your x, y, z, your x0, y0, z0, that's your initial point, and your a, b, c, there's your direction vector. So you can read off information by just, if you're given it in this form, you can say, aha, I see my point, I see my direction vector, I'm good to go. Vice versa, if we have our point and have our direction vector, it's super easy to write that in that form. There are other ways to write lines. One of the ways you might possibly see, and I'll just mention it here, but we don't talk about it nowadays, is called symmetric form. And symmetric form, someone said, you know, I don't like this extra t. So the word parametric means that there's a parameter. And so that parameter t is allowed to change. And so we're going to talk about parametric equations. That's going to become a topic in the near future. So you might say, well, is there a way to write a line without having to resort to t? And the answer is yes. And what you do is you start with parametric form and you actually solve for t. So for example, in the first equation, you'd get x minus x0 over a. But you'd also get, if you go to the second equation, y minus y0 over b. And in the third equation, z minus z0 over c. And now what you do is you cross out that t equals, and then you have this expression, which is a relationship between x, y, and z. So this is called symmetric form. The thing that's challenging with symmetric form, it's not as easy to work with and as intuitive. That's why we tend not to talk about it these days. But physicists perhaps might, because they're not intuitive and easy to work with. So, all right. Now, one thing to note is that when we talk about the line, we have to be a little bit careful here because there's a tiny bit of ambiguity. And so what you can do is you could pick a different starting point. Or you could say, I don't like this direction vector. I want the direction vector that runs in the opposite direction. Or I want one that's a unit vector or something else. So there's not a unique starting point. There's not a unique direction vector. And because of that, you might do the problem. The person sitting next to you might also do the problem. Your answers may look different, but you can still both be correct. So just keep this in mind. that there are many different ways to express the same line. Okay, so let's do a quick example. Let's find the line through some points. So we need to have some points. What are some points for us?
0, 0, 0.
Let's not do 0, 0, 0. Someone said something like 901. Something like -2. I'm going to guess that's -2.
3, 1.
3. Let's not do 1. Let's do 1. Yeah, okay. All right. We'll do that. 901 and -2, 3, 1. So, now we go into our mindset. We're looking for a line. We say, well, if I'm looking for a line, I need a point and a vector. Do I have a point? Yeah. In fact, I have 2 of them. So a point, good. I'm great. So I go to my next thing. Do I have a vector? Not yet. But what can we do? We can make one. So the way we have to figure it out is to say, okay, given the information we have, how can we find a vector? Now, this one, I will say it's kind of quick. Sometimes you got to work a little bit. But this one, all right. So what's a vector? Well, I can choose the vector between these 2 points. So let's go from 901 to -231. So the vector, well, how much do I change? 9 goes to -2. What's the change? Yeah, I went down by 11, -11. 0 went to 3, +3. 1 went to 1, 0. And it's okay to have vectors with changes of 0. Now, we say, well, let's write our answer. I prefer parametric form, so I'm going to write x equals, y equals, z equals. And then there's the 2 parts. There's the point, and there's the vector. Well, which is the right point to use? Should I be using 901, or should I be using -231?
Either one.
Yeah, it doesn't matter. Either one will still give me the same line. So let's suppose I went with 901. All right, so there's my point. Then plus, now I have my point. Next thing is the vector. So that's the ABC part. So, well, there's really right now only one vector. But so what do we have? Plus -11 and 3 and 0. And then that's multiplied by our t. Okay. So, again, point, vector. And so we could say this is 9 minus 11t. We could say 3t. And we could say 1. And you might say, am I allowed to just have the coordinate z be 1? Shouldn't there be a t involved? No, it's okay. It sometimes happens. It's just saying that z isn't varying. And that's okay. That's all right. All right. Well, let's try something a little more interesting. So suppose we have a point and a line. So I have a point P. There's my point P. I have a point Q. And there's this line that passes through Q. And I'm even going to tell you the direction vector of that line. That's the direction vector V. What I want to do is ask the following question. How far is it from P down to the line? So I need to find a direction. Now, this is not one of those, this is totally obvious what to do things. This is one of our, let's think of the geometry things. So what is our tool that we've recently learned about? Vectors, right? Let's start with vectors. All right. We have one vector. We have a vector v. Let's make another vector. What's another good vector to work with? Well, someone said, hey, let's make a vector perpendicular to v. Now, in 2 dimensions, that's okay. But in 3 dimensions, how many vectors are perpendicular to a single vector? The answer is a lot. There's infinitely many. So the problem is that if we go to 3 dimensions and we want to think 3-dimensionally, there are many vectors perpendicular to v. In fact, we'll be using that in the near future. What's a vector that's really easy to get? Well, The vector that's really easy to get is the one between the 2 points. So let's mark that vector. Now here I'll draw it from Q to P. Not that it really needs to be from Q to P. I could do it from P to Q. But the reason I want to go from Q to P is I'd like to put these two vectors next to each other so I can talk about the angle between them. So there's some angle sitting there between those two vectors. Now we say, aha, what do we have here? We have a triangle. But it's not just any kind of triangle. What kind of triangle is it? It's the right kind. It's the kind we like. All right, so now we say, perfect. I have a right triangle. There's this angle theta, which we'll deal with in a moment. And I know the hypotenuse. I don't know the adjacent side because I don't know where this point where the line drops from P straight down to the line is. I just know V sort of points somewhere in the direction of this line. All right. Well, given that I know this, let's see. I say, okay, I have an angle, I have the hypotenuse, and I'd like to know something about the opposite side. What relates those things together? The sine function. The sine relates the opposite and the hypotenuse. So we can say that sine of theta is equal to the opposite side, which we don't know, over this length, if you will, the length of the vector of Q times P. So now we're in business. Whatever we're looking for has to be equal to this magnitude of Q times P times sine of theta. The problem is, of course, I don't know what sine theta is. So now we start thinking to ourselves, okay, let's go back and think about where have we seen a sine theta before, especially a sine theta between two vectors. And we start thinking and wondering, is anything starting to cross our mind? Yeah, it showed up in the cross product. So in particular, suppose I were to multiply by the magnitude of V and divide by the magnitude of V. Certainly I could do that because that would just be multiplying by 1. Then what we see is the following. That what we're looking for, this numerator here, that's the geometric interpretation of the cross product. And in particular, it's the magnitude of the vector from Q to P cross with the vector V. And then downstairs, I have the magnitude of V, which we can interpret as the magnitude of V. And that's it. So the length we're looking for, that formula, it turns out it's related to a cross product. Now, I don't memorize the formula. I just figure out how to get to it. In fact, there's something even more clever, which is we can find this point. But that's a different story, and we'll get to that later on. Okay, so let's do a quick example. Let's find the distance from a point. So we need a point. What's our point?
-3, 7, 5.
-3, 7, and 5. All right, and we need a line. So x should equal, in parametric form, so it's something plus something t.
1 plus 7.
1 plus 7t. All right, y?
-3 plus 5.
-3 plus 5t. And z?
7 plus
7 plus 6t. All right. Probably these numbers are going to be terrible, but that's okay. That's okay. The point is the process. So, what do we have? Well, what's the vector v? Can we read that off? Where is v at?
7 plus 1.
Yeah, it's this. You read off the coefficients of t. So, v is 7, 5, 6. All right. Now, what else do we need? Well, here, this is our P, negative 375. Where's our Q? Well, right, we need a point on the line. Is there some point on the line?
Yeah, you just put it.
We could plug in 0, and in particular, if you just read off those numbers, 1, negative 37, this could be our point on the line. So there's Q, there's our V. So if we go Q to P, what do we have? Well, 1 to negative 3, that's negative 4. Negative 3 to positive 7, that's plus 10. 7 to 5, that's negative 2. And therefore the distance, we take the magnitude of QP cross V over the magnitude of V. And we probably should take that cross product really quick. Okay, so QP cross V, I, J, K. You probably can guess from what we're doing here that we should get really good at doing cross products because we're going to do these a non-trivial number of times. And the answer is yes. You should get good at doing these because you will be doing them a non-trivial number of times. So, plus 10I and plus 24J, leaving us with 70, 10, negative 90. All right. Well, I did that kind of quick. If I were paranoid, what should I do now? I should check, dot product. 490 plus 50, that's 540, minus 540, minus 280, plus 100, plus 180. All right, so it works out. On a side note, this is 10 times the vector 7, 1, negative 9. So when I take the magnitude of QP cross V, I can really say, oh, this is 10 times the magnitude of 7, 1, negative 9. So if I see a common factor, I can pull it out. Downstairs, we have the magnitude of 7, 5, 6. And so we end up with 10 times the square root. Upstairs, that's 49, plus 1 is 50, plus 81 is 131. And then downstairs, we have 49 plus 25, which is a big number, 74, plus 36, and 74 plus 36 is, where is that, 110? Yeah. All right, and there you go. So it's 10 times the square root of 131 over the square root of 110. And that's the distance. It's some number. All right, so we can find it. Normally on an exam, we get to find nice numbers. Okay, so that's lines. But there's more. Okay. Well, the other thing are planes. And for planes, these are going to be sort of our preferred flat objects for most of the class. So we really like planes. Essentially, you can think of, if you're going from 2 dimensions as lines, in 3 dimensions, it's planes. You want planes. Plain and simple. So what do we have? Well, suppose I want to find a plane. Now what I need is a point, and I want to have a single direction. But there's a little bit of a caveat, because the question is, well, what's the direction of the plane? It sounds like it's an easy question until you start to think about it a little bit. So you could say, well, if I'm in the plane, I can actually go in lots of different directions. So there's lots of directions which are contained inside of the plane. Think of the plane as like a floor. And if you think about the floor, you can go all sorts of different ways. So there's not a single direction you can go that's in the plane. But now let's think about the floor. Again, we say, aha, there is one vector which is unique in terms of the floor, which is the vector that stands perpendicular to it. That's straight up from the floor. So we call that the perpendicular vector. Well, really we call it the normal vector. So whenever you see the word normal going forward, you should think of, that's really code for perpendicular. So when we talk about the direction for the plane, the direction that we use is the perpendicular direction to everything in the plane. So there's going to be some vector coming out of our plane, and that vector has this amazing property that it's perpendicular to the plane. Now what's nice about this is it gets us down to saying there's a single direction that we have to work with. And we can start talking about things about planes. We can say, well, look, two planes are going to be parallel to each other. In other words, they're not going to intersect if their normal vectors are parallel to each other. So you can think of it like the first floor and the second floor of a building. Both of those are parallel to each other. They don't intersect if you were to extend them out. And they both have the same perpendicular direction, namely going up and down. You can also talk about the angle between planes. So you can talk about, well, suppose two planes intersect. What's the angle of their intersection? And the answer is, well, look at the angle between their normal vectors. And so that's how we're going to work with them. Now, that's all well and good, but the question is, how do we actually describe an equation for the plane? So think of the picture. We have an initial point, x0, y0, z0. So here is that point. Because remember, we said a plane has a point and that normal direction. So we have that point, and then there's this perpendicular thing to the plane. My normal vector, it's a, b, c. Now pick any other point at all. Any point you want in the plane. Has to be in the plane. X, y, z. And we make a vector. So from x0, y0, z0 to x, y, z. This is a vector that's in the plane. In fact, we can write it down because we just say, what's the change? X minus x0, y minus y0, z minus z0. That's the vector between those points. And what do we have? Well, this vector that's in the plane and this vector that's perpendicular to the plane are perpendicular. And if two things are perpendicular, their dot product is 0. So we get that 0 is equal to the dot product of the normal vector with this change. Well, if you multiply this out, that becomes a times x minus x naught plus b times y minus y naught plus c times c minus z naught. Now, the way we usually do this expression is we say, well, let's rearrange it. So we put the variables ax and by and cz together, and then there's all these other terms which aren't varying. They're fixed. They depend on the plane. So you get ax naught and by naught and cz naught. So the generic formula for a plane is something of the form ax plus by plus cz, and then you get that's equal to a constant d. Now, you can think of what that constant d is it's moving the plane up and down. So that's what d does as you vary d. It shifts the plane up and down through space. It locates it. The other side, there's a really important thing to observe. Notice these coefficients here, a, b, and c. And notice your normal vector, a, b, and c. These are really close to each other. In fact, a lot of people would say they're the same thing because they're the same thing. So that normal vectors are really easy to read off formulas from planes. And if you have a normal vector, then it's easy to generate the plane. Because now you have the coefficients, you can get the ax and by and cz, and then you plug in any point, and that helps you solve for d. So let's do a really easy example. Let's hope it's easy. Find the normal vector for the plane, 2x plus 5z equals 3 plus 4y. All right. So remember, we're looking for the coefficient of x, y, z. So is the answer 2, 4, 5? Someone was quick to say no. It's like, okay, because you've become very suspicious. Whenever you hear the instructor say, this is easy. Good for you. You should always be suspicious. All right. Well, what's wrong with this equation versus that equation? Yeah, see, the y is not together with the x and z. So what you should first do is say, wait a second, let me write it in the right way. 2x minus 4y plus 5z equals 3. Now I have in the form something x and something y and something z equals a number. Now we can read off these coefficients. So what is the normal vector? 2, negative 4, 5. And life is good. All right. So let's try another problem. Okay. So let's suppose we're given a point P, some point, and a plane AX plus BY plus CZ equals D. Find a formula for the distance from P to the plane. So in other words, I want to find this length here. All right. Well, interesting times. Let's think about this for a moment. There's lots of ways to do this, and we'll do this in a couple of probably different ways over time. We're just going to focus on a nice, simple formula for now. The problem is we don't have the point on the plane that's closest to the point that we're given. If we did, life would not be so bad. It's just a distance formula. We don't have that point. And in fact, the way it's given to us, we haven't been given any point on the plane. But there should be lots of points on the plane. So for now, let's just suppose I have a point. Even though I don't know what it is yet, I'll call it x0, y0, z0. I could probably find at least one point on the plane. Okay, so there's a point on the plane. So what I can do, that's not so bad, is I can talk about the vector. So, I don't know, let's do that vector. So I can do a vector from my point x1, y1, z1 to x0, y0, z0. So the change in x, change in x, I got them backwards. Change in y, and the change in z. All right, there we go. x0 minus x1, y0 minus y1, z0 minus z1. All right. What else do we know that's not in this picture yet? Okay, someone has said we know the vector for the plane. Now, let's be careful. Which vector do we know for the plane? The normal vector. The normal vector. What is the normal vector for this plane? ABC. Where does ABC fit into this picture? Well, the answer is that ABC, it's a perpendicular direction. Now, I can put ABC anywhere I want. I can say, well, maybe it's right here. Let's just put it right there. Now, it's almost certainly not going to be just the right length to get all the way down, but it's going to be some length. All right. And since I have two vectors, I can talk about the angle between them. So now we think about what we have. Well, there's a hypotenuse, which in theory we can find. There's the angle between these. What side do I want to find out information for? The adjacent side. And if we were to add in this side, of course, there is a triangle here. So what relates an angle with the adjacent side and the hypotenuse? The cosine does. So what can we say? Well, we can say that cosine theta is equal to, it's the adjacent side, which we don't know, over this magnitude of this vector here, x0 minus x1, y0 minus y1, z0 minus z1, which we also don't fully know yet, but okay, so that's what we have. All right, so we're making progress. So what we're after, our distance formula, is this vector here times the cosine of theta. Now, the question is, can we write this in a better way? Well, is there something that relates vectors and the cosine of an angle? Now, dot is something we should remember. What? The dot product relates vectors and cosines of angles. All right. So, what do I need? Well, I have one of my vectors here. So, if I were to put in another vector here, let's say ABC, and divide by that vector ABC, then I'm good to go. Now I have a dot product. Now I should say there is one small technicality which I've brushed aside temporarily, and at some point I'm going to need to address it. It is quite possible that my picture is not 100% accurate. And you're probably thinking, I know. Most of your pictures are incredibly inaccurate. In that here I drew it so that the angle theta was acute. It could be that the angle for the vector ABC was pointing up, and then the angle theta would be obtuse. So that cosine theta could actually have been a negative value. So technically, we should be putting absolute values here. Now we can just say, okay, we put the absolute value there, and that solves everything. That's just a small technical note. Now, believe it or not, the hard part is done. And I hope you believe that. Here's the beautiful thing. This is a dot product. So we can write this as ABC dot this vector. So x0 minus x1, y0 minus y1, z0 minus z1. Take the absolute value of that and divide it by the magnitude of A, B, C. All right, upstairs, well, this would be A times x0 minus x1 plus B times y0 minus y1 plus C times z0 minus z1. Downstairs, it's the magnitude of A, B, C. All right. Now we do a little bit of work. So multiply this all out, and I'll regroup. So I get AX0 plus BY0 plus CZ0. And I subtract off AX1 plus BY1 plus CZ1. And I divide it by, well, I'll say the square root of A squared plus B squared plus C squared. Because that's what the magnitude of ABC is. Now, so far we're okay. And we say, look, we were given A, B, C. That's part of our initial problem. We were given x1, y1, z1. That's part of our initial problem. What weren't we given? We weren't given this point. So right now, we sort of have this extra information that we'd have to figure out. Or do we? Mwahahaha. Very mysterious. Mwahahaha. Okay. I claim that AX0 plus BY0 plus CZ0 has a beautiful simplification. What is it? It's D. Why is it D? Well, look at it. It's a point in the plane. And therefore, it satisfies the equation for points in the plane. And any point in the plane satisfies A times the x coordinate plus B times the y coordinate plus C times the z coordinate is simply D. And now we can say that our desired length is equal to the absolute value of the value D minus AX plus BY plus CZ divided by the square root, AX1, BY1, CZ1 divided by the square root of A squared plus B squared plus C squared. And that's the answer. All right. Now, Do you memorize the formula? No. It's not about the distance formulas today. We're building up our geometric intuition. It's easier to remember how to derive the formula. But again, we're going to see probably even better ways to get to our information that we want. But this is just to help us get our mathematical juices going. All right. I think we have time for an example. Now, the reason I say that today's lecture is so important is that we like to have the problems where we say, all right, suppose we give you this information, find a line, or we give you this information, find a plane. So there's a bunch of examples here, and I can say definitively we might get through the first one. I'll do the rest later on. You can watch them as you are want. The good news is you'll get to do a whole bunch of these on those quiz prompts. So you're going to get really good at this stuff. So this is what's important. Given information, you're given points, you're given lines, you're given planes, you're told they have to satisfy certain things. They intersect, they're perpendicular, so forth and so on. One is contained inside the other. How do you find the desired line, or how do you find the desired plane? So this is what you want to start practicing. This is what you want to start building up to. So let's start with something that's not so bad. Find the equation for the plane containing the 3 points. All right, so we need 3 points. Okay, quickly, 3 points. 4, 9, 2. There was a 0, somebody said. -5, 7, and? What? 1, 2, 3. Okay. So, I did not know these points ahead of time. So if I find it, then we know the process works, It's not just rigged. All right. So we have 3 points. So just think of the picture. And again, it doesn't have to be a great picture. We just have to build up our intuition. So what we have is we have 3 points sitting out in 3-dimensional space. We say, okay, we go through our checklist. We're looking for a plane. What information do we need if we want a plane? A point and a direction. It's always going to be the same. A point and a direction. Do we have a point? Yeah, we have plenty of points. So what do we need? A direction. All right, so here we go. We know we have points. We just pick any one. That's fine. So the next thing we focus on is the direction. And the direction, that's the big thing about a plane. So I say, all right, we need a direction that's perpendicular to the plane. It hasn't been given to us. What do we have? Let's figure out our information. We have 3 points. So one of the things we can say is like, okay, because we have this really cool tool, this cool tool is called the cross product. The cross product tool says, instead of having to look for the vector that's perpendicular, start looking for vectors that are inside. And if you could find 2 vectors that are in your plane, 2 different vectors, then what can you do? You cross product, and that gives you something perpendicular. So what we can say is, all right, we don't have to look right now for the perpendicular direction. Can we find 2 vectors that are inside our plane? And the answer is, yes, we can. How do you do it? Yeah, pick one of your points and find the vector to the 2 other points. So, suppose we pick the vector 492 as our corner point. So 492 to 0, 5, 7, how much do we change by? Yeah, we go down by 4. And then 9 to -5, go down a lot. -14. 2 to 7? 5. Okay, so there's 492 to 0, -5, 7. Now, 492 to 1, 2, 3. -3. -7, and 1. So these 2 vectors are vectors in the plane. Now that I have 2 directions in the plane, we cross. Because if you cross 2 directions in the plane, you have to find something perpendicular. And the something perpendicular, that is the normal vector. So this will be I, J, K, -4, -14, 5, -3, -7, 1. Okay, so we get minus 14I, minus 15J, plus 28K, and then minus 42K, plus 35I, and plus 4J. So this would give us 21, negative 11, and negative 14, if we've did that right. And, did we do that right? Well, quick check. Negative 63 plus 77. Well, that would be 14. Subtract 14. Oh, that's a good sign. Minus 84 plus something. No, it's 154. Come on. Minus 70. Yeah, okay. Yeah, so that's right. There you go. Good. Life is good. All right. Phew. Okay, now, this is our normal vector. Now, what's our answer? Well, take the normal vector. Those are the coefficients. 21x minus 11y minus 14z equals something. Something. The question is, what's in the box? What's in the box? So what do? Well, okay. What haven't we used yet? Well, we really haven't used our points yet. We used our points kind of to find the vectors, but remember that last thing, that d value, helps you locate the plane in space. So you need the point to find d. So how do you find d now? Plug in a point. Which one? Which is the point that will give us the one that you need? Any of them. So for example, 1, 2, 3. You get 21 times 1 minus 11 times 2 minus 14 times 3. Well, that's 21 minus 22 minus 42, which is negative 43. So the answer, 21x minus 11y minus 14z equals negative 43. Now our time is basically up, but if you were paranoid, what could you do so you were like, I am 1,000% convinced we did the right answer? Plug in the other points. Because all 3 points have to be on the plane, not just the one you use. And if all 3 are there, you're guaranteed the right answer. And then if they're not, you're guaranteed you get to go back and do more work. So again, just to double check, we plugged in the point 1, 2, 3, and that's how you got this. But you could, again, plug in one of these other points. So suppose we plug in 0, negative 5, 7. So we'd have 0 plus 55, because that's negative 11 times negative 5 is a plus 55. And then negative 14 times 7 is negative 98. Well, if you take 55, you subtract 98, what do you get? And the answer is, you get negative 43. 55 plus 43 gives you 98. So it's a check. So we got the 1, 2, 3 to get the constant, and we can check the constant by plugging in a point. And similarly, if you're very patient and you plug in 492, 21 times 4, that's 84, of course. 11 times 9, negative 99. And 2 times 14, negative 28. So what do you have? Well, we have 84 minus 99 minus 28. So that's really 84 minus 127. Well, if you take 84 subtract 127, how far apart are the numbers? The answer is that they're 43 apart, but of course the 127 is larger, so it's negative 43. So we are now 100% for sure. This has to be the plane. There's no other choice, because we've checked every single point is actually on the plane. So life is good. All right. Find the intersection of the following 2 planes. Well, we don't have any planes, so we've got to make some up. So we will probably live to regret our following choices, but all right. So we write some planes. X plus 2y minus 3z equals 5. And now we need what? 3x minus y plus z equals 7. All right, there's 2 planes. And so what is it talking about, the line of intersection? Well, so suppose you were to sort of sketch these 2 planes and ask the question, well, what's happening? So I'm going to attempt to provide a somewhat reasonable sketch of what's happening here. And so what tends to happen is when you have these 2 planes, if they're not parallel to each other, and this is a case when they are not parallel to each other, they'll have a common line. So in other words, a single line which runs through both of them. And so we want to find that line. And so our goal here is to say, well, what's the line? So when you're looking for a line, what do you need? Well, for a line, we have to find 2 things. We need a point, and we need a direction. So we start thinking about what to find. Let's focus on the direction first. So what's true? Well, if we think about the picture here, we say, looking at the picture, we have a line, and this line has to have the following. It has to be in the first plane, say this bluish plane. So that means that the vector, which is the direction of the line, has to be a vector in that plane. Now if you look at the somewhat more pinkish plane, you can make the same statement. The vector that has to be the vector of that line has to be inside that pinkish plane. So the moral here is that the direction is the direction which is common to both planes. So direction common to both planes. All right, so how do we use that information? Well, now, what does that mean? Well, whenever we think of planes, we always think to ourselves of normal vectors. So let's think about what the normal vectors are. Well, it's 1, 2, negative 3, because we can read off these coefficients, and 3, negative 1, 1. So these are not the directions of the line. For one thing, the line should only have one direction. These are 2 different directions. What these are directions of the normal vectors. Now, the definition for the normal vector is it's perpendicular to the plane. In particular, this normal vector has to be perpendicular to the line, and this normal vector has to be perpendicular to the line. So now I have 2 vectors which are both perpendicular to the vector I want. So both of these vectors are perpendicular to the direction of the line. So here's a fun fact. So we'll make it over here, fun fact. And you can tell it's a fun fact because I wrote the word fun fact. So if we know 2 vectors which are perpendicular, which we write that little symbol there, to the vector we want, then we can find our vector. And the way we do it, we can find our vector by the cross product. All right, so there's our fun fact. Good pieces of information to know. So if we have 2 vectors that are perpendicular to the vector we want, we cross them together. That gives us the direction we're after. Therefore, take the cross product of these 2. That gives us our direction of our line. So I, j, k, 1, 2, negative 3, 3, 1, 1. So I times 2 times 1, 2i. J times negative 3 times 3, minus 9j. K times 1, plus k. 3 times 2 times k, that's 6k, but we went the other direction, so we subtract. 1 times negative 3 times I, it's negative 3i, but we went the other direction, so we add, minus, 1, 1j. So that would be plus j, but we went the other way, so we subtract. And so you end up with 5, negative 10, negative 5. All right. Now, the nice thing is we really don't care about the length. So if you see anything in common, factor it out. 1, negative 2, negative 1. When in doubt, quickly double check. 3 minus 2 minus 1, that's 0. 1 minus 4 plus 3 is 0. So we can use this as the direction of the line. We don't need the 5. So that's great. We've got our direction. What's left? Do we have our line? And the answer is we don't have our line. This is one of those rare instances where the point can be tricky. So what's the challenge? Well, I know the direction of the line, but that's not enough. I got to somehow nail it down. So how do I go about nailing down my point? And the way to do it is to say, look, I just have to find just one. If I can just find one value for x, y, and z that satisfies both of these equations, life is good. So what we're going to do is we're going to find just one. And you might say, but there's too many. There's too many variables, x, y, and z, and there's not enough equations. And we're going to use that to our advantage. So we're just going to pick a value for x. Let's pick x equals 0. So suppose x equals 0, and I want to satisfy both of these. So I need to have 2y minus 3z equal to 5, and minus y plus z equal to 7. Now, we do some sort of manipulation. So here's something we can do. Let's multiply the bottom equation by 2. We can do that. So 2y minus 3z equals 5, minus 2y plus 2z equals 14. And now if you add the equations, the 2y's cancel, minus 3z plus 2z gives us z, and we end up with z equals 19. But now that you know z, you can solve for y. So we have negative y plus 19, that's got to give us 7. So what can y be? Well, the answer is it can be just one thing, which is 12. Excuse me. So y should be 12 and z should be 19. Well, why not? Let's double check, just to make sure we're okay. All right, 2y minus 3z. All right. Oh, made a mistake. Notice we added incorrectly. It's negative z equals 19. So z should be negative 19. All right. Well, okay, now we fix that. So, okay, now let's put it into here. Negative y minus 19 equals 7. And we can add 19 to both sides. Negative y, 7 plus 19. Well, that would be 26. So y should be negative 26. All right. Now let's check that. So plus 26 minus 19 does equal 7. And then minus 52 plus 57 does equal 5. So that our point that we need for our line is 0, because that was our choice for x, comma, negative 26, comma, negative 19. Now, is this the most elegant point? Absolutely not. We just need a point, though. So, what's our final answer? Well, in parametric form, x equals y equals z equals, first the point, 0, negative 26, negative 19. Then the vector, 1, negative 2, 1. So plus 1 times t, plus negative 2 times t, and plus negative 1 times t. And there you go. All right, well, that's not so bad. What do? You look for the direction, you look for a point. And this fun fact, by the way, gets used over and over and over. Now, it's not the only fun fact, but it's such a good fun fact that you will be like, hey, let's try that. And we'll be like, what a great idea. That works. Okay. So let's try another one, because we have more. There's always more. All right. Find the equation for the line which passes through the point, and we'll just pick a point here. Let's say 3, negative 2, and 5. It hits the x-axis, all right, and does not, whoops, that says line, it should be lie, in the following plane. Well, what's the plane? Well, okay, we'll make up a plane. All right, 4x minus 6y plus C equals 139. All right, there you go. So let's think about what's happening here. We have a plane. And so there's our plane. All right. And then we have a point. There's our point. And now what we want to do is we want to find a line that goes through the plane. Oh, nope, sorry. This shouldn't be lie. This should be, and does not intersect. I am so sorry. There we go. I knew I had the wrong word. Does not intersect the following plane. All right, good. Now that I can state the problem correctly, so we can't hit that plane. So what does that mean? Well, in other words, this line can't be like, and hit it. No, that'd be wrong. So what has to be true is that whatever the line turns out to be, if we were to extend forever the plane and the line in both directions, and really in all directions, they never intersect. Well, what does that say about the line? It says the following, is that if you were to actually come down and sort of imagine pushing the line down, that it runs parallel to a line that's in the plane. So, the moral is that the direction of the line has to be perpendicular to the normal vector. So what's the normal vector? Well, 4, -6, 1. All right, so that's good news. So we know that the direction of the line has to be perpendicular to 4, -6, 1. We don't have a second fact, though, about the direction of the line yet. So let's see what else we can figure out. We know a point and that it has to hit the x-axis. Now, hitting the x-axis actually gives us useful information. Because what does it mean to hit the x-axis? Well, it means that if we think about it in terms of the picture, you have this point here, 3, -2, 5, and then you have some point here that's on the x-axis. And a point on the x-axis looks like something like a, 0, 0. So, I can do the following. I can say that the vector for the line has to have the following form. Namely, I can look at it as the vector 3 minus a, -2, 5. So for some choice of a, that's the right vector for the line. That's the direction of the line. Now, let's put these two pieces together. We know the direction of the line has to look like that for some choice of a. We know that that direction has to be perpendicular to the normal vector. So what's true about two vectors which are perpendicular? The answer is that their dot product is 0. So combining these two pieces of information, we can conclude that 3 minus a, -2, 5, dot 4, -6, 1 has to equal 0. So we work this out. So we get 12 minus 4a. Then here we get plus 12 again, plus 5 has to equal 0. So doing the dot product. Now 12 plus 12 plus 5 gives 29. And move the 4a across, 29 equals 4a, or a equals 29 fourths. Good. So what does that tell us? Well, it tells us that the 29 fourths, that we can be used to find the direction of the line, and the way you do it is you take this information here and you plug it in to that direction. That's the direction of the line. So you get 3, which is 12 fourths, subtract 29 fourths, and if you take 12, subtract 29, that gives you minus 17 fourths, -2, 5. And that's the direction of our line. All right, good. Now, are we done? Well, what do we have? We have our direction, and we were given a point. And therefore, we can find the line. So, in parametric form, x equals y equals z equals the point, 3, negative 2, 5, 3, negative 2, 5, and then the vector, so it's minus 17 fourths t, 2t, 5t. The point, the direction vector. And now we have the parametric form for our line. And it satisfies both. It won't intersect the plane because it runs parallel to the plane. That's what this dot product guarantees. It hits the x-axis because we rigged it so that it's going to pass through the point A00. And therefore, it satisfies everything that we need, and that's the answer. Well, that was a fun one. That one's kind of not so bad. Good question. We like good questions. Okay. Find the line which perpendicularly intersects the following line. All right, well, we need some space. Well, we'll write it in vector form. X, y, z equals 1, 4, negative 2, plus t times, let's say negative 1, 3, negative 4. There you go. There's the line. So it has to perpendicularly intersect that line, and it has to lie in the following plane. Well, what is that one going to be? Well, let's choose 3x plus y minus z equals 2. All right, nice numbers. Well, it doesn't mean the answer is going to be nice, but at least the numbers are nice to start. All right, so let's think about the picture here. So we have a plane, 3x plus y minus z equals 2. So here's our plane. And then we have this line, and it's going to intersect the plane. It's coming in, so here it comes in, it hits, and then it passes through. All right, so this line. We want to find a new line, and it has to satisfy the following. It has to, first off, intersect, and it has to intersect perpendicularly, and it has to be in the plane. So it's going to intersect, so it's got to hit that point, because the line has to be in the plane, and it has to hit that point. And then the angle of the line, well, it's such that we form a right angle with the line that came through, but also that we're in the plane. So let's think about the direction of our new line. What has to be true? Well, we know it's got to be perpendicular to this line because it says it's perpendicularly intersecting. So it's got to be perpendicular to negative 1, 3, and negative 4. It also, this line here, has to be in the plane. And any line in a plane has to be the case where the direction vector is perpendicular to the line. Sorry, the direction vector is perpendicular to the normal. So it has to be perpendicular to 3, 1, negative 1. Now, we say, wait a second, we have that fun fact. I'm perpendicular to two things. And if I'm perpendicular to two things, then it has to be the case that I can figure out what I'm after by taking the cross product. So we're going to take negative 1, 3, negative 4, cross 3, 1, negative 1. Now if we do that, what do we get? I, j, k, negative 1, 3, negative 4, 3, 1, negative 1. So that would be minus 3i, then minus 12j, and minus k. Wow, this is a very negative expression right now. Going the other direction, minus 9k, and then it'll be plus 4i, and then it'll be minus j. So it looks like we're getting 1, negative 13, negative 10. Now, of course, we check. 3 minus 13 is negative 10, plus 10, 0. Good. Minus 1 minus 39 is negative 40, plus 40, 0. Good. So there's our direction. Well, that's half the line. Where's the point? You might say, hey, there's the point, right? 1, 4, negative 2. The problem is that some point on the original line, it could be over here. That's probably the point. And so that's not the right point. We need the point where the line hits the plane. So we think to ourselves, okay, well, what's true? Well, let's think about our line for a second here. Now, our line, we can write this in parametric form. And in parametric form, we could say a point on the line looks like 1 minus t for x, 4 plus 3t for y, and negative 2 minus 4t for z. So the 1, 4, negative 2, that's the point. Minus 1, 3, negative 4, minus 1, 3, negative 4. That's the direction. Really, we're just reading off the entries component-wise. So that's what a typical point on the line looks like. And the thing is, I have to be on the line and in the plane. So what we want to do is we want to combine the plane with the point. The way we do it is we just plug x, y, z into the equation. So if I'm on the plane, it has to be the case that 3 times 1 minus t plus 4 plus 3t minus negative 2 minus 4t has to equal 2. So we're replacing x, y, z by x, y, z. Multiplying that out, 3 minus 3t plus 4 plus 3t plus 2 plus 4t has to equal 2. The 3t's cancel. These 2's actually cancel there. We get 3 plus 4 is 7. Move it across. 4t equals negative 7, or t equals negative 7 fourths. What that means is that when t is negative 7 fourths, and we plug it into this, we get a point which also satisfies this relationship. So in other words, it's a point on the line, and it's a point on the plane, so that's going to tell us our intersection point. So we plug in negative 7 fourths into our expression. So 1 minus negative 7 fourths, that's 1 plus 7 fourths, that's 11 fourths. For y, well, we're going to get 4, which is 16 fourths, subtract 21 fourths. 16 subtract 21 gives us negative 5 fourths. And finally, we're going to get negative 2, and then negative 7 fourths times negative 4. Well, that's negative 2 plus 7. And so that tells us that z is going to be 5. Well, that one was actually kind of nice. Of course, very conveniently, the 4's canceled. So, we're ready to put our answer together. We have our point. We have our direction. So, we write down x equals y equals z equals. We take our coordinates for our points, 11 fourths, negative 5 fourths, and 5. And then here we go, direction plus t minus 13t minus 10t. And we're done. And there's going to be a lot of questions like this, and a lot of these are just geometry. Think about the picture. I'm parallel to something. I'm perpendicular to something. What are the directions that I know? Can I introduce a new vector? How do the vectors relate to one another? How do I find a point? What does it mean for a point to intersect a line? And when you start thinking about these things, you build off of them, bit by bit. And they're not always so obvious. We like to think, oh, 3D, that's obvious because I live 3D. But it takes a while. But it does come. Keep practicing. Keep at it. You'll get it. Good. Good.